I started a little bit. I did comp methods first. They're done. I still have to go ahead and do yours. Yes. No? So I think that this is working. It is. Okay. So our final exam is on 3 note sets, 12, 13, and 14. Most of this is kind of mathematical. Note set 14 is much more of a vibrations thing with the multiple degrees of freedom, stiffness matrices, mass matrices, but we're going to start off trying to understand arbitrary forces. This idea that instead of having a cosine or a sine wave or no forcing function at all, how do you handle that type of response? Does that make sense? So, if you also want me to answer any questions, please raise your hand and let me know if you're confused about anything. I'm going to try to go through this not super fast, but because it is review, we will skip over some of the minor details and also point out things that I don't think are important for you to study. So, in general, we've done free vibration, which has motion dependent on what? The natural frequency. What causes the motion? Initial conditions. That's correct. So if there's no force on it and the mass is just hanging out, it doesn't move. It will only move if you provide some sort of input energy in the form of a stretching of the spring or compressing of it, that's potential energy, or I hit it with something and provide it an initial velocity. Those are the free vibration ways to start motion. The other thing is force vibration, where we looked at it with the sinusoidal input. We've done all that math. That was from the previous exam, where we had a sine wave or a cosine wave. We can assume a solution for the differential equation. We can do something like the complex response method to determine what x of t is. But then the next question becomes, what if you have multiple forces acting at the same time, or forces of a very strange variety? And we jumped into the idea of superposition first, which basically says that if I have one forcing function, this will produce one deflection response. So F1 of t, it'll produce a response x1 of t. If I do F2 of t, it'll produce a response x2 of t. If those two forces were to act at the same exact time, what would our total response be? So if both of these things are acting at the same time, what is our total response? Yeah, x1 plus x2. When is that allowed? If the system is linear. What does that mean? Thank you, Peter. You have to do these 2 tests for it. That's correct. So we originally discussed this idea of a linear operator, L of x, where I will apply that operator to some variable. And to determine if it's linear, we have to do these 2 tests. The first being that if I were to plug into my linear operator some constant, could I pull it out and get the same result? So for example, a derivative is a good example of that. Let's say our linear operator is d dt. If I were to do the derivative of 4x, this would be the same as 4 times the derivative of x. That passes that test. Do you see that? I gave you a question on your last quiz, I think threw some people off, where I said, okay, let's say I tell you an operator is something like x plus 4. That's a linear function, right? That's a line. But the question was, is it a linear operator? And it's not, because let's think about why. So if I do the L of Cx, that would mean I plug Cx into this operator. That would be Cx plus 4. Do we buy that? The question is that equivalent to pulling the constant out? So if I do C, the linear operator on x, that would be C times x plus 4. Are those two things equal? No, they're not, which is why this is not a linear operator. I know that seems kind of weird because it's a line. But in regards to this concept of linearity, if you include this extra term, it ends up causing it no longer to be linear. This is really important in the design of sensors because a lot of times if you're doing a linear type of device, what you would like is that, okay, let's say I have some pressure sensor. I apply 10 pascals to it, I get a voltage output. If I apply 20 pascals, the voltage output should be doubled, right? Double the pressure, double the output. But if you have something like this in your response, that screws up that idea. So the concept of linearity is very important for that type of thing. And obviously it's important for vibrations where we need linearity to do things like superposition. No, because you might have something like x squared that looks like it's kind of multiplied, x times x, but that's not a linear operator. That's the first test. The second test is that if you were to add the summation of x and y, can you separate those operators? Basically saying we know that ddt or whatever is a linear operator. If I were to do x plus y, that is equivalent to dx dt plus dy dt. Specifically? No, for the derivative. Oh, you mean a linear operator that doesn't work by? I mean, the example I give in the notes, yeah, something like sine. If I do sine of x plus y, is that the same as sine of x plus sine of y? No, it's not a linear operator. If it fails one of those tests, automatically not a linear operator. It needs to pass both. Is that okay? It's not one or the other. It has to pass both of them. Okay? Okay. So, the impulse response function. I go through this proof here where I basically show, okay, if we drop a mass on an object, that's going to cause motion to happen. I drop this mass from some height that has potential energy. That will be converted to kinetic energy. What do we do to kind of analyze this in regards to once this thing hits, what does this mass do? What kind of analysis do we do from physics? Huh? Momentum, right? This was a momentum type of problem. Momentum occurs, we typically do that for collisions. And essentially what we learned, again, I wouldn't stress too much about this proof, like this concept, like this specific proof of dropping the thing I'm not going to test you on. But the thing that is important is the fact that that hit is essentially the same as providing an initial condition to the system, an initial velocity. That's the equivalence. So the idea, and I'll write this out shortly, is that you can take this hammer or this mass and drop it, and instead of doing that problem, you can have the two masses statically sitting, and then I provide some initial velocity. It'll end up being exactly the same result. Are we okay with that concept? We've seen this in the homework, where you have some sort of force response, that's an impulse. You can make that equal to 0, and then apply an initial velocity. That's the motivation here. So we defined what an impulse was. It's based off the change of momentum. That's kind of why we looked at that dropping problem to begin with, to relate momentum to an impulse, where the impulse by definition is F delta T. This is the impulse. What are the units of impulse? Newton second. Force times time. Newton second. Hopefully, hopefully. So that is our definition of an impulse. And based on that definition, what we derived was that the initial velocity of the system can be written in terms of that impulse. Because like we said that F delta T is equal to the change in momentum. If you were to assume that the mass is not moving before it struck, you can say that this is equal to the velocity times the mass after the collision versus the one before the collision. So this is after, this is before. If it is not moving before, this term is zero, which means we can say the velocity immediately after the collision is the impulse over the mass. We will represent that as the initial velocity of the system. Any questions about this concept? So just to kind of summarize this, if I have mx double dot plus kx is equal to some impulse, and a lot of, or I don't want to say impulse, it's equal to some force. Let's say I make it the Dirac-Delta function, which we haven't talked about yet, but let's say it's that. For that specific problem, we'll assume that there's zero initial conditions. I strike it with a hammer, it starts to move. This whole thing is equivalent to mx double dot plus kx is equal to 0, except this time we have this velocity, which is f hat over m, where f hat is 1 for Dirac-Delta specifically. Like for this problem, I said it was Dirac-Delta. These are equivalent statements. Mathematically, you end up getting the same result, which is very convenient because we know how free vibration problems work very easily. That was exam 1 stuff. Depending on your damping, if you're underdamped, overdamped, or critically damped, you go look to see what the response is in general based on constants and say that's your initial velocity. Then you can find out what your displacement will be due to that impulse. Does that make sense? Thumbs up from people that understand that. Okay, perfect. So you don't need to worry about this proof. This is honestly, I hate this proof. I'm going to remove it from the note sets in the future. It's kind of a waste of time. It's arbitrary. But essentially what we learned is that the impulse itself is describing the strength of the forcing function. So if I were to write a differential equation like mx double dot plus kx is equal to delta of t, that forcing function is the impulse of 1. If I were to have the same exact differential equation, the only difference being I now have a multiple of that. What that 7 does is increase the impulse by a factor of 7. So now instead of having an impulse of 1 Newton second, you have an impulse of 7 Newton seconds. So based on how big that impulse is, that'll dictate the strength of that forcing function, how much of an impact it has on your response. Yeah, like that will change the amplitude. We'll see that in a second, how f hat ends up changing the amplitude of the motion. The motion itself will be the same frequency, same type of damping, but how high does that peak go depends on how hard you hit it, which should make sense physically. Like if I do a little baby kick versus somebody else doing a major kick, then yeah, it's going to deflect more, but it will deflect at the same exact frequency and stuff, because that's all based on the system, not based on the external force. So what we learned is that if I were to plot the impulse, I might have some impulse that's, at some time tau. You know what I'll do? Because this is not direct delta. This is some general impulse. This is force versus time. Here's some impulse that I have centered at tau. And don't forget, we write that like this, where we shifted it to the right, f of t minus tau. That minus tau is a shift in time. What does that mean physically? If I have a mass and I have a hammer, what does that mean if I have t minus tau? Yeah, shifting it to the right mathematically speaking. What does that mean from a physical perspective? I'm ready to hit it, What's that mean? It's delayed. So somebody starts their stopwatch. Go. I'm waiting. Okay, now I hit it. Some tau seconds later. It's delayed. So that is what this means here. This shift to the right is that delay in hitting it. Both. Well, it's one and the same, right? It's not going to respond to the hit until I hit it. Right? It's just sitting there. Once I hit it, now it'll start to move. There's no delay between the hit itself and the mass moving.
You dropped an anvil from 5 stories up. It's going to take a while to hit the ground.
Versus like a foot up. Exactly. There's some delay as to when that impulse happens. So because this is force versus time, and we know the impulse is F delta T, that is equivalent to the area under the graph. This is the impulse, is the area under the graph. Which makes sense. You're thinking about units. I have force versus time, newtons versus seconds is the area of that rectangle. Okay? Okay. Now, the main type of forcing function we talked about in terms of an impulse was the Dirac-Delta function, which is kind of the standard, the baseline mathematical technique to determine the motion of the mass. So if I were to have some sort of Dirac-Delta function, let's say this is time versus force again, a lot of times you'll see this represented by just an arrow. That arrow has what height? It has an infinite height. And then the width is what? Basically 0. And obviously everybody knows that if you multiply infinity by 0, you get 1. Don't know. It's a math thing. It's a mathematical technique. It's not a physical thing. We cannot have an infinite force. We cannot have 0 time. But we basically say that the area under this curve is equal to 1. This is the Dirac-Delta function. We've seen on the second exam, that extra credit question, and also in your homework, if you're not integrating over that arrow, there's no impulse, right? So that's a question I've repeated twice now. This idea of if I were to shift the Dirac-Delta function, let's say to the right, by tau, if I'm only integrating from T1 to T2 and they're both less than tau, well, it hasn't integrated the impulse. There's no contribution yet. The mass hasn't been struck. So there's no impulse. Does that make sense? Okay. So again, I have this bolded here. In general, the Dirac-Delta function is the force that causes an impulse equal to 1. Is that okay? Need that to be clear. Once that impulse equal to 1 strikes the mass, what does the mass do? It moves, obviously, but it moves at a very specific way. It moves at an impulse response function. That's a definition. The impulse response function is the result of striking the mass with an impulse of exactly 1. that okay? Okay. So this is what we had for our initial velocity before, f hat over m. Again, we can assume some free vibration problem with this as the initial velocity. And I give an example for an underdamped system. If you look at your equation sheet or go all the way back to note set 5, you can see that this is the response of an underdamped system. What's different about an underdamped system compared to critically damped or overdamped? Underdamped oscillates, that's correct. So if I were to draw this, it would look something like where it would oscillate back and forth as it decays exponentially. We see that we have this sine wave here that's dictating the oscillations, and then the amplitude of that motion is created by this envelope. That's based on, let me switch the colors around. That's the sine wave, and this thing in the front dictates the amplitude of the motion. What does A depend on? A, the amplitude, depends on the initial conditions. So coming back to your question, if you have 7 delta t, your initial velocity is bigger, that A will be bigger, which causes the amplitude of your motion to be bigger. But it still decays sinusoidally and exponentially. Is that clear? Matt, is that okay? So again, these equations are on your formula sheet. I expect you to be able to know how to use these in general. I know it's from the first exam, but again, this class builds on itself. So I expect you to be able to use these. But for this impulse, we'll say that x naught is 0 because the mass is just hanging out. So all the terms with x naught go away. So that goes away. That goes away. And then this goes away. Also this, but what's the phase? That's 0. So what's the phase? 0. What is the amplitude? V naught over omega d. That's correct. This is V naught over omega d. What is V naught? F hat over m. That's correct. This is F hat over m omega d. That is your amplitude, the damped natural frequency. So that's the frequency it'll oscillate at. That depends on the damping. That's omega n times the square root of 1 minus zeta squared. So if zeta is 0, it oscillates at its natural frequency. If it's not 0, it oscillates a little bit differently. So for an impulse caused by the Dirac-Delta function, what is A? Yeah, it's 1 over m omega d. F hat is 1. If I have 7 times the impulse, we see that our amplitude is 7 times as large. We buy that. Yeah. Omega d is omega n squared root of 1 minus zeta squared. So zeta is the damping. If there's no damping, it oscillates at omega n. If there is damping, it'll oscillate at a frequency smaller than omega n, because that will be a number less than 1. That ends up being a little bit slower in its oscillation. Are we okay? So we see that here. If we come back to our underdamped solution specifically, this was the amplitude A. So we see that F hat causes a larger amplitude. And then again, the other stuff is still the same. Now, specifically, if it's the Dirac-Delta, we see that that F hat becomes a 1. So this is the impulse response function. This thing is h of t because of the fact the impulse is specifically equal to 1. That is what makes it the impulse response function. Thoughts, concerns? Are we okay? Halo, are we okay? So again, because of the definition says that we care about this impulse response function. This is just a baseline. Like, we need something to share amongst the engineering community as just a standard response. We will say that that response specifically is when the impulse is equal to 1. That's how the mass moves. Now, if I move at some other impulse, it's just a multiple of that. So 7 times would be 7 times that. That makes sense? That whole thing is h of t for an underdamped system specifically. Sure, because it's the same exact type of thing. The only difference is you would have a different equation, but you'd still use the same initial velocity. You'd still solve it in the same type of way. So the impulse response function, that is what it is called. Specifically, again, Dirac-Delta causes an impulse of 1. Impulse of 1 causes impulse response. That's the train of events. Is that okay? So what we see is that this is the response due to any arbitrary impulse because of the f hat. You can see that I rewrote it with an f hat in the front. And what we learned is that x of t, no matter what the impulse is, will be the product of the impulse and the impulse response function. Again, it's just a multiple of it. I thought you're on Teams. I thought you were on Teams. All right, Connor, time for you to come join the party. Connor's on Teams. Charbel says you're a loser for not coming to class. So, this makes sense. Again, specifically, the impulse of 1 is h of t. If I were to multiply that by some factor, a bigger impulse, it will still decay at the same exact rate, just with a larger amplitude. Let me draw a picture to show that. So let's say that this is my impulse response function, and then it dies out. If I hit it with a bigger amplitude, you can see that the red one is the impulse response function with an impulse of 1. It's underdamped, so it's decaying. The blue is exactly the same, except bigger amplitude. That's the only thing. It might take longer to decay also because of the fact that it has a bigger amplitude. But I didn't draw that perfectly here. This is going to cause an echo. Now I see your face. Let's take a second to appreciate this. All right. Now I have him staring at me. This so, oh my God. Does that make sense? Now, the only thing that really changes is that depending on when the impulse strikes, all that happens is that all of these functions get delayed by that amount tau. So again, let's say here's my normal system. Here's the impulse response function if I were to delay it. I thought you guys shared laptops and now you logged in. Oh my God, this is a disaster. Pay attention. So if the impulse strikes at 0, let me draw a picture of the impulse. So this is time. This is x of t. This is time. This is the force. I am saying that you have this impulse hit at time equals 0. You even see you have an initial velocity. That's the initial slope of the line, right? Now imagine that instead of striking it at time equals 0, I strike it at time is equal to tau. Oops. So again, this is x of t. What does that look like? Exactly. It's the same exact shape. It's just delayed. So this will not be moving at all. And then when tau hits, now it'll do its thing. Do we see that? So that's why we need to include this t minus tau in here. Because when tau is equal to t, this essentially reduces back to that exponent being 0. That's as if we're starting the motion at that point in time. Does that make sense what I just said? Omar's give me a head nod. Jerry? So, if we compare this to the undelayed one, so this is when tau is equal to 0, meaning it's the left picture here. I just struck it. When does this exponent equal 0? At what time? 0, right? When does the sine wave inside equal 0? 0. Now, because of the delay, when does that match for the bottom? When does this exponent equal 0? When t equals tau. When does this sine wave argument equal 0? When time equals tau. So it ends up matching identically to this, except we're delayed by tau. It has the same exact response. It's just that your time will not start until the strike happens at tau. Then you have the same exact behavior. Hanging out. Chilling. It's not doing anything. Huh? I didn't hit it yet. So the mass is just hanging out here, doing nothing. I'm waiting. Then I kick it. Now it starts to move. I'm mad at it. Didn't study. Don't point at her. It's you. Oh, Ramez. I thought you were pointing at Tess. So we do some examples here where we say I gave you what the properties were. I said an impulse force of 1,000 newtons applied for 0.01 seconds. And again, units are your friend. So this is in newtons. This is in seconds. Neither of these things are the impulse because the impulse has units of Newton seconds. It's the product of the two. So we find the product. If we see that this product is 10, the way that we can write that as a differential equation is to say that we will have mx double dot plus cx dot plus kx is equal to 10 times the Dirac-Delta function. Right? Dirac-Delta function has an impulse of 1. This problem had an impulse of 10. Therefore, I'll just write the right-hand side as being 10 times bigger than delta. Yes. Thumbs ups. Cool. So I plugged in some numbers. We're able to find what the natural frequency is, what the damping is, do a little bit of math. And the easy way of doing this, well, there's two ways of doing it, but the way that I would recommend doing it is to say that V naught is just the impulse over M. That's the initial condition, F hat over M. Then you'll use that. We know it's underdamped because of the damping. And then you can determine what the response is of that mass. How do we feel? Feeling good? Yeah? Pumped? Cool. That's the general definition of the impulse response caused by the Dirac-Delta. Now, the reason that that's so important and the biggest thing here is to understand that x of t is based on the impulse multiplied by the impulse response function. Note also when f hat equals 1, they are equivalent, the response and the impulse response function, because it moves it that way. Yes. Yeah.
That's for linearity on the formula sheet or not?
No, it will not. You have to know those tests. So the next motivation was we have some arbitrary force. So if you look at the axes, this is time on the x-axis and force on the y-axis. And this random thing here, now you're on Team Stiff. Were you listening to it in the car? Yeah. So if you see f of t is this random thing that I drew in blue, maybe there's no useful way to solve the differential equation if I set the right side equal to this complicated function. So what we do instead is model this function as an infinite amount of impulses. You have an impulse here, you have an impulse here. All these things are impulses. I go through a proof here, which you don't need to memorize or do. Where essentially what we're looking at is how each of those impulses contribute to the total displacement of the mass. So now imagine I have like 20 little kids with one mass, and they're all going crazy because they're at a birthday party or something. And one person kicks it, and they all start freaking kicking it like this. All 20 of them are going nuts. Each one of their kicks is causing this mass to displace in a certain way. Probably a more legitimate example is the piñata, which is swinging like a pendulum. So if one person hits it and somebody else on the other side hits it at a different moment, the combination of both those impulses will cause the total response of the mass. Now, instead of envisioning it as two discrete hits, hit number one, hit number two, imagine that they are infinite. There's an infinite amount of hits happening for that pendulum, or for that piñata, that pendulum. So what we can do is find what the little response is from each of those individual hits. And because of superposition, we can add all those little responses together. So every single one of those little responses can be added. That will give us the total response of the system. You see the flow here of this note set? We start with superposition first to say that the total x of t is the sum of x1 of t and x2 of t. We discussed Dirac-Delta to describe an impulse and the impulse response. Now we're here, where we will find what the individual contributions are to each of these little impulses. And because we're assuming it's a linear system, we will add them together to give us the total response of the mass. Is there any confusion about that? Thumbs up from people. Pedro, you okay? Andrew, thumbs up. Logan? Jerry? So, what did this ultimately lead to? Convolution, which for vibrations is important because we want to go ahead and determine what x of t is for any arbitrary force. So again, this thing here, f of tau d tau, is like an impulse. That's f times delta t. That's an impulse multiplied by the impulse response function. This kind of looks like f hat h of t, except we're integrating it across the entirety of time from 0 to some arbitrary point. Yeah, tau is all the time. We're integrating with respect to tau. What this is essentially doing is allowing us to shift from one impulse to the other. So if you think about dx, if you're integrating something with respect to x, what you're doing is summing little rectangles, where you're integrating from 0 to 5 on the x-axis. So you're starting at 0, you're integrating in increments of dx from left to right, and then adding up those contributions. Same deal here. We are adding up these individual impulses multiplied by the impulse response function. That will give us the total response of the mass. confusion. Matt.
This equation, you did not have it with the minus tau go.
Yeah, that's correct. It ends up being commutative. So what we see is that depending on the complexity of the problem, it might be in your benefit, if you're doing it by hand, to apply the t minus tau to f or to h. You end up getting the same result. It's a nice property of convolution. Is that okay? That's something we mentioned before. You've seen it in your homework. And I show you this star symbol. That's the convolution symbol between the force and the impulse response. I didn't mention the Duhamel integral in class, or Duhamel, I don't know how to say it. That's just the dude's name who came up with this. It's just a convolution integral. I'm not going to mention it on the exam. Some people ask me about it. It's just the name. Don't stress about it. So I do an example here where the force is F naught, and I give you some impulse response function that is T. Meaning that if I were to strike some system with a hammer with an impulse of 1, this is what it'll do. And I tell you it's not physical. Why isn't it physical? Yeah. This isn't, no, this is the force. This isn't a square sine wave. It doesn't have to be sinusoidal. It depends on the damping. Let's pretend this is some random case of damping that's not under damp. Or there's no damping at all, maybe, where h of t is t. What happens? Yes. Sure. Why not? Why can't we physically do it? Not that. Adra. There's no acceleration. Well, this is actually physically possible. This is okay. I mean, not the complete thing. You'll have some sort of rise time. I'm talking more about h of t. Why isn't this physically possible, Chad? Right. So imagine I hit the mass, and this is saying that it'll move based on t. So at t equals 1, it's at 1 meters. At t equals 2, it's 2 meters. It's just going to keep going after one hit just forever. That doesn't make physical sense. Where's that energy coming from? Where's the pull back from a spring? Yeah. What'd you say? Okay. Thank you. Yeah.
Unless you're in space.
Unless you're in space. Yeah, this might be physical in space. There's the sun analogy too. You're in space, the sun. It's all working out. You guys are collaborating. I like it. So what we did in this problem was to find x of t. You plugged in tau into one of them and t minus tau into the other. So I said f of tau, which in this case is just a constant. It's f naught. That doesn't change. And then the impulse response, remember h of t was just equal to t. So I do h of t minus tau. That just goes into whatever t was in the original one. That becomes t minus tau. Are people okay with this concept of a function? This throws some people off. I want to make sure that we're on the same page when it comes to what a function is. So once we do that, we can integrate. We can multiply that f naught if we'd like, or take it out of the integrand, whatever you want to do. Once you do that, it'll end up giving us what the response of the mass is due to that specific force. So h of t is when you have an impulse of 1 striking it. This is the specific response if you have this Heaviside function being used. Yes. That I probably shouldn't do that. If that was a homework problem, it should have been capital F of t. I didn't want to confuse that with F naught. So that's my fault. But in this case, they're the same. That's a good question. I do the same exact example where we switch it. f of t minus tau for this example would be what? What was the original f? It was f naught. What happens if I plug t minus tau into it? Huh? It's still f naught, right? This is still f naught. H of t for this problem was t. So what is h of tau? Tau. I can integrate that, and that'll give me the same exact answer. Am I going too fast? Are people lost? Tracy, you good? Again, all that math is there. I do a more physical example where we still have the step function. The only difference is that it is delayed by some amount t naught, which means that nothing happens until t naught. The mass is just sitting. Then at t naught, it's pulled to f naught. Huh? So for an underdamped system, we already showed this earlier. This is the A. This is the amplitude, which was V naught over omega d. Again, V naught for Dirac-Delta, or for any impulse, F hat over M. For Dirac-Delta, F hat is 1. That leads us to this expression, 1 over M omega d. See that? Delaney? Is that okay? Okay. So we could take H of t and convolve it with that force, which is F naught. And in this problem specifically, we see that it is 0 from 0 to t naught. And then it's F naught from t naught onwards. So if we're going to do the convolution integral, which goes from 0 to t, I split it up into 2 sets of integrals. One that goes from 0 to t naught. What's f of tau when it's 0 to t naught? 0. This integral ends up not being important. And then we integrate from t naught to t. So that will be the response of the mass. So if we integrate that, and note, well, it's done here. I did h of t minus tau. You see that all the t's that were in the underdamped response are now t minus tau. If you go through and integrate that, you end up with this very ugly expression. I wouldn't expect you to integrate something like this on the exam. It's a little too much. It's not really worth it. I'll test your integration skills with Fourier series, not with this. So what we learned here is that as t went to infinity, this other term ends up going away, which shows that x of t ends up being f naught over a k. What is that? That's a static deflection. So remember, I have this constant force F that's pulling on this mass. When I first jolt it, it might oscillate a little bit, but ultimately, if this force is just here, and it's like 6 newtons, I pull it, it might be oscillating to get here, whatever, and then eventually, it's just going to be at exactly the position it needs to be based on a static force of 6. And we can see that in this graph here. First thing we note is that nothing happens until t naught, which in this mathematical example, I say it's 1. It jumps up, it oscillates because it's underdamped, and then eventually it'll just hang out at its static deflection, which depends on what the stiffness of the matrix is, right? Do we buy that? Emery? Sure. Any confusion about that example, ask again, Michael. We're not letting it go. We're just pulling it. We're jolting it. Because of that jolt that happens at t naught, it is surprised, and because it's underdamped, it ends up oscillating a little bit about that point. Yes. So like I apply some constant force. Like I pull it, and then because of that pull, it might go past, and then it'll oscillate about that position, and then eventually it'll settle to that static position.
Mass on the spring and you turn on the magnet.
Yeah, that's a good analogy. If I have a mass on the spring standing up, and I turn on a magnet above it, it might just go up, and because of that jolt, it'll go past that static point. It has potential energy at that point that'll convert back to kinetic, and it'll go back and forth until it's at the static spot due to that force that's holding it in that position. And I go through a scenario here, except where you include initial conditions, which means that you have to include the free vibration response of the mass. What is that called? Let's assume you have damping. What's that called? What's it called, Lucas? Why is it called? Logan, what is it called? I phone a friend. Pick someone. Lucas, pick Lucas. What is the free vibration response called? The transient or the homogeneous, but specifically I was looking for the word transient. So if we have a free vibration response, we want to include that in our final answer. That's assuming we have initial conditions. Steady state. That's when the force is applied and now it just moves based on the force. That's a steady state. Coming back to this picture, all these oscillations are the transient. And then the steady state will just be it hanging out due to that constant force. So same type of deal. You have the free vibration. In this problem, there is no damping. So it just ends up being the sum of A sine and B cosine. That's the free vibration response. This is free and homogeneous. While this thing is the particular, or the forced. And the particular. So you can do convolution first, get what the particular response is, and then do initial conditions. Yes. If one of them is not zero, you would have to do this. Because you don't know what A and B might end up being. There are equations for it on the formula sheet, I think. But you might have to show it and be like, okay, if I plug in 0 into this, once we have the total solution, I can solve for A and B. Or plug in 0 into the derivative to solve for A and B. You're given initial position and velocity. One of them might be 0, the other one might be a number. So it just depends. If they're both 0, then it doesn't exist. So I do this example here where I give you cosine of 2t, which you could solve using the stuff we learned for exam 2, complex response, or assume a solution for the particular. But I told you I wanted you to use convolution. And so we integrated cosine of 2t. Oh, h of t. F was given. This is f of t. How would you find h of t? Huh? Using the stuff given on the left. More detailed than that, though. How would I find h of t? Well, it depends. Depends on the damping. It's undamped. How would I go about finding h of t? Yeah, I got to find the impulse response. That is h of t. Thank you. That's more what I'm thinking about. What'd you say, Char? Not 1, to delta. So to find h of t, set set the right side equal to delta. Do we understand why? H of t is the impulse response due to the Dirac-Delta function. This is a property of the system and has nothing to do with the actual force in this problem. So I replace that force with delta of t. Now, how do I find the impulse response? You don't want to assume a solution for this. Not sure what you mean by that. How would you prove it, though? I tell you in the exam, find it for me. How do you find it? We just talked about this before. Anybody? Stop saying words. I want you to prove that to me. That's only valid if it's underdamped. That's what it is. How? What do I change? Well, the m in this case is 1. This is a force vibration problem. What is an impulse equivalent to? V naught. X double dot plus 16x is equal to, not V naught. I'm converting a force vibration to, Ben, help me out. Nope, not help me out. This is equal to 0 with an initial condition of F hat over M. So that part was correct. Remember what I said earlier? The force vibration response with delta of t is equivalent to the free vibration response with the initial condition of with the initial velocity. Does that make sense? I need some feedback here because there's a lot of wrong answers. You got to start studying. Huh? It's clicking. That's what I wrote earlier. Force vibration response. I can convert this to free vibration, assuming the initial velocity is based on the impulse. This is so important. I'll give you that. But it's your responsibility to know I can convert this force vibration problem to a free vibration problem by converting the initial velocity to F hat over M. Do we see that? So if you do that for this problem, this x of t is based on the undamped case. You can go look at your equation sheet for what x of t is for an undamped response. And there's a bunch of ways of doing this, but one way is to say it's a sine omega nt plus phi. Oops. A sine omega nt plus phi. This a ends up being v naught over omega n. And this phi ends up being 0 because x naught. What is x naught? 0. We assume there's no initial position. So that means that x of t will be v naught over omega n sine omega nt. So what's h of t? Huh? Yeah, so the v naught f hat over m. So what is f hat for h of t specifically? 1. So this thing is f hat over m, which will be specifically for the Dirac-Delta 1 over m. So in this problem, what's m? 1. What's omega n? Somebody who hasn't answered yet. What's omega n? Yeah, I know you know it. It's 4. That's correct. Remember, mx double dot plus kx equals 0. If I divide by m, I get x double dot plus omega n squared. So this ends up being 1 over 4 sine of 4t. That's h of t. So if you come back and look, that's what we get for h of t. That's one way of getting it. If you convolve, you get your particular solution by integration. And then we'll go ahead and apply our initial conditions to this total solution, which is the homogeneous plus the particular. So again, this whole thing here, this is the homogeneous. I could have also written a sine omega n t plus phi, but this is another way of representing it. And then you end up getting your total solution. We see that. I recommend for studying purposes to do this problem. I think it's a useful problem and explains multiple things. You're using initial conditions, you're doing homogeneous and convolution. There's a lot going on. Yes. Or where I was writing. Here. Yes. That's correct. Change the notation. Chad. This is in note set 12. This is the last example in the note set, example number 4. And note set 12. But just to kind of summarize this whole concept, I give you some system. So I give you some mass attached to a spring and a damper. From an experimental perspective, if I were to hit this thing with the Dirac-Delta function, it will oscillate at its impulse response. So I strike the system with a hammer, measure the displacement, I have the impulse response function. Experimentally. Granted, you can't actually do f hat is equal to 1 in real life, but this is the idea, if you could do this in theory. From a math perspective, what you'll do is write the pre-vibration response. This is very blurry. You take your force vibration with delta t on the right, make it free vibration, except you use an initial velocity based on the impulse, f hat over m. If it's Dirac-Delta, f hat ends up being equal to m, or equal to 1. Sorry. Then you have your impulse response function. You solve that x of t when impulse, with the initial velocity being 1 over m. Once you have that, you can convolve h of t with f of t, whatever the force is, to give you what the response of the system is. So again, I apply any arbitrary force to the system. I can convolve them. That will give me the x of t for the arbitrary force. Jerry. No. The force was cosine. Where is it? The force was cosine. If you need to find h of t, that is the specific case where the force is Dirac-Delta. So you have to do that on your own. When you find h of t, then you'll convolve it with this force. That makes sense? Yeah. That's your arbitrary force that is acting on the system. You cannot find x of t unless you know the impulse response function. This is your f of t. To find h of t, if you didn't have it available to you, you have to convert this to a force vibration problem with delta t as the force. Perfect. It clicked. Clicking is good. I recommend looking at this chart and understanding this. This is the procedure. This is in the note set. I think it'll help conceptualize things better. And I go into words about what that means. Questions about note set 12. I know it's dense. I know it's a difficult note set. I need you to read this and understand it and do problems. The problem's in here. The problem's in the homework. I posted practice quizzes for all of the note sets. They're all online now. Any doubts? Canvas, under quizzes, or under modules, under practice exam and quizzes. Questions? Okay, let's take a 10-minute break.